First, they were sort of balancing. Now, because that star has become compact and the heat generated by the compactness of the star is transmitted to the outer part, so that then expands the outer part. So that outer part no more remains with their body, but it starts expanding. And because when it expands, the temperature of the outer skin gets reduced. It will, like sun that we see today is white, it gives almost a yellow light that we all see. But when it starts becoming bigger and bigger, the whiteness will sort of reduce and finally it becomes a red giant. A very huge structure it will become. Most of the inner planets like Earth and Mars, all these will become, the expansion will be so much that all these planets will be part of the sun body itself. And then eventually this gets away, gets expanded further and gets released. And then another 5 billion years or so, our sun will turn into a dwarf, a very small star, very bright though, brighter than the sun that we have today. It will be more whiter light at that time, but it will be very small. So that is the life of star, of our star sun, and so is the life of most of the stars that we see in the sky. They all have. And then from there, if it is a massive star, at the end, it will not be that it becomes a, because when the iron gets formed inside the star, the energy which is created there is so large that the gravitational force cannot withstand, and there is an explosion that is called supernova explosion. And then other stars here. So that is the kind of cycle going in the celestial environment, and the more and more stars get formed and they also die. So a lot of change occurs everywhere. Now let me talk about the structure of the sun briefly. This is our sun, and this is the region. One is the core of the sun, where the fusion reaction takes place, where the energy, because of the fusion, the main source of energy is this region, one. And then beyond this, outward, there is a region which is called radiating zone. In this, the density is so large that nothing can penetrate directly. So the energy which is created here is given to each particle, and the particle gives to next particle and next particle. So that is the radiation process that goes on till a very large part of the interior of the sun. And then comes a region where the density is slightly lower, where the material can move. And that is called convection zone. Convection is nothing but like when we boil water in a patili or in a pot, you can see that the hot water, and if it is a transparent one, especially nowadays there are those transparent water heaters are available. So there you can see that the water which gets heated from the bottom goes up and then goes down. So there is a circulation. So that kind of circulation goes on in this part of the sun. And so because it is by convection, so this region is called convection zone, and it transports energy from here to here by convection. And that gives energy to this outer part, the photosphere, which we see. And because the temperature is around 5,000–6,000 degree Kelvin, so we get white light. Because the emission depends on the temperature, as I mentioned before. So, and on this, there are on the outer surface also, this is photosphere on Earth, which is called core, and on this there are spots. You can see those sometime by a very small telescope, even binoculars, but not that one should not see it directly looking at the sun. You should try to project it by a small telescope on wall or somewhere, and the image that is formed from the wall, there you can see spots. And this number, I will also talk about it a little later. And on this there are also prominences like here, that if you see it face on the sun, they appear like black filaments, but when they go on the edges, there they look very bright, and we call them prominence. But it's as so many of these things happen on this outer part, and there is a thin chromosphere and transition region and a very large corona. This part of the sun, the chromosphere and the transition region and the corona, cannot be seen by naked eye. It can be seen when there is a total solar eclipse, and the moon covers this photosphere completely, because the diameter, apparent diameter of the moon and the sun are more or less the same. So when they get aligned such that the moon disk covers the entire disk of the sun, then we don't get light from this photosphere. And then there, the region on the earth where you don't get light directly from the photosphere is covered to you, that we call total solar eclipse. And where this total solar eclipse happened, there you see the corona and also the chromosphere for a very short while. But today there are lots of satellites which are sent to space, and in this space you can do this by that if you have a telescope in space, and then from there you, while taking the photographs of the sun, in front of the camera, if you put a small disk such that the photosphere is just covered, so then this part can be seen there, can be photographed. And lot of research, in fact, the images that Avnish is using for his research project are the images of the sun, and mostly in the ultraviolet region of the sun, where the photospheric light is not there. It's not by that there is a disk there, but they put a filter. They remove the photospheric light by filter, and there is no scattered light in the space. So then you can get X-rays, you can get ultraviolet rays, you can just image sun in extreme ultraviolet. Some of those images I will show in the next two slides. So this is what the sun is like. And as I mentioned that there are spots on the sun. Here there are two images of sun. This is one of Mars 2001, which is called, when there are more spots on the sun, we call that solar maximum. And when there are no spots or very few spots on the sun, we call it solar minimum. This is about five years later. This is 2001, and this is 2000, January, this month. So almost 5 years later. And like this, each day, the spots, their position, their number, slightly get changed. It also changed because of the rotation, which we will talk about later. There is also, like our Earth rotates, the sun also rotates. So the spot also rotates. And these, if you take a very detailed picture by satellite, the telescope and in the satellite, you can take very detailed picture of these little portions of the sun, which we call as the sunspot. And there you can see that even these have structures. The spots, their number change, their area change, their shape also get changed, the size, everything changes dynamically with different times. And they also take work, they evolve. The spot would be smaller in the beginning, and then confuse later on. They erupt. When they erupt, that's what we see as solar flares. And these solar flares disturbs our ionosphere, magnetosphere, and the magnetic field on the earth, the communication system, the TV and the radio communication, they all get disturbed because when there is a large eruption on the sun, in these or in the filaments or prominences that are there, these are called very active events on the solar surface. There are also radio bursts that suddenly there is some explosion on the surface of the sun, and it emits lots of radio emission. So you get disturbance in your radio communication, in your radio signals, which are used for communication. So they get disturbed very well. So, and the number of spots, there are counted. There has been a program going on for past 40, 50 years regularly. They count the number of spots. They also measure the area of these spots. And if you make a plot here, this is a plot for about 1900 to 2000, for about 100 years. Observation of sunspots. And the sunspot is low here, it rises, becomes low again, rises. So these are called maxima, minima. These are the top is called maxima, and the bottom, the least number, is the minima. And most of these minima and maxima, they occur at the saturation of about 11 years. The difference between a maxima, average distance from here to here or here to here in terms of time, is about 11 years. And so is the case with the minimum as well. And that we call as the solar cycle. And though there are good activity, very dynamic features occur on the sun when it is at the minimum and it has very less number of spots, but sometimes those number of spots also can give very large flares. But when it is maximum, that is the time that the sun is more active. It gives more coronal mass ejections, more flares, and that is why it is called maximum and more dynamic sun at that time. So a lot of research work is being carried out on these. And here is an example of sun in X-ray. There was a satellite called Yoko, Japanese satellite, which was making observation of sun in X-rays. And this is of solar maximum time. And then they have arranged these images up to, not all images, but some selected images as a function of time. From here to here, about 5.5 years. So 5.5 years after, you see that the emission, X-ray emission is very less. So that is called solar minimum, and this is solar maximum. So not only that you get the number of spots more and less, the X-ray emission and Agni is trying to study sun, and in the extreme ultraviolet band, there are 4-5 frequencies on which large amount of data is. So he is trying to see the radiation as a function of time of the extreme ultraviolet emission of the sun. Here, this is basically, there are few images of the sun. They are displayed in the form of a movie, and then you can see that spot is from one image to the next image, it's moving. So this was that the spot does not remain stable on the sun, was the first indication that the sun rotates. And this rotation, the rotation that you are seeing here, of course, there you see as if everything is moving at the same time, but if you do careful analysis, you will find that the spots which are near to the equatorial region, they move faster. The spots that are on the polar side on north or south, they move slower. And this kind, like our Earth rotates around its own axis, but it's being a solid body, so it rotates in 24 hours everywhere. But Sun is not a solid body; it is a gaseous plane, and because it is a gaseous plane, can afford to have differential rotation. So the sunspot, because they are there at different latitude of the sun, they differentially rotate. The spots which are near the equator, they rotate fast. They take about 24. Apparently, they take about 27 days, but that is apparent motion because our Earth also rotates with the sun, orbits the sun. And if you calculate, if you remove the apparent rotation which has come there because of the Earth's own orbiting around the sun, that is about 2 days. So that the 2 days gets affected. So the equatorial part physically moves around itself in about 25 days. And this part, the polar part, takes about 30-35 days. And this has a variability. So a lot of research work has been done on this, and there is also a very important aspect of solar research is that how these spots get formed. We don't understand. They form, they change, they move, all that is known. But how these spots really get formed, that the scientists, no scientists really understand. So there is a sort of a scenario which says that our sun has a what is called colloidal field. From one pole to the other pole, there is a weak magnetic field. And as I just shown and was talking, that there is a differential rotation. The equatorial part of the sun moves faster, the poles move slower. So then what will happen? If there is a magnetic lines of force which is straight, because of this motion, the equatorial part of the field line will get curved, will get ahead, and the polar points will lag behind. And if that keeps on going for many rotations, so there will be a sort of twisting of magnetic field. And this magnetic field, when, like suppose you take a rope, and from one end you hold, and the other hand, from the other end, if you keep on rotating in one direction, there will be a lot of twists that will come on the rope, and eventually the rope will break. So that this twisting of magnetic field lines and the magnetic loops get formed, and these then so become like small regions on the sun, and then the colloidal fields. And again, this magnetic loops which get created in the form of sunspots, there is a process on the solar surface called flow. That combined with that flow, some gets closer to the equator and disappear. They sort of merge each other, and then the colloidal field again gets converted to colloidal field. So in this scenario, so this is not the theory, but this is most accepted theory for the formation of sunspots on the solar surface, has given a very big importance to the study of differential rotation of the sun and also the heliocosmology, the study of this interior sun. A lot of research work is being done on that worldwide and in our country also. We explored the region, the differential rotation of the sun in the outer part, mostly the outer part of the world. I'll tell you why we did that. And on that, so these are, this work began in something like 95 when our radio telescope got closed. So then I got interested in studying the solar rotation in the sun. And from there, a lot of work has been done. In fact, 3-4 students have worked on this and published very good papers. In fact, one of them was to come here. He works in a private university here, Jaidev Sharma. He recently used, there is a satellite called Solar Dynamic Observatory in this. And there is also another satellite called Stereo. So he used data from these two satellites and done his PhD just last year and published very. In fact, his work has been the most important work that has been done under my supervision in the last 20-25 years. So very good work he has done. Now let me give some glimpses of this work that we have done. And before I do that, let me also tell you briefly how the rotation is basically measured. There are 3 ways to measure the rotation of the sun. Like we don't feel our earth is rotating, but it is rotating. And we get this feeling by the sunrise. Every day sun rises from the east and sets in the west. It's not because sun moves, it is because our earth rotates around its axis, right? Similarly moon. So we don't feel that our sun is rotating, but the small picture that I showed with few slides, a few images of the sun, you could see that the spots are moving. So that method where you take a spot today and measure its position on the solar surface, and 2 days later you see the spot has moved, take that position, and then from there you determine how much is the angular rotation of the sun. So this method is called tracer method, that you trace the objectives of the spots on the sun. In fact, such programs can be easily done by a very simple 3-4 inch telescope that you put it somewhere and make the image on the wall or a screen, and then you get the image there, the spot, you put a paper there and mark the position of 1 or 2 spots today, and after 2 days or tomorrow day after, keep on doing that. And there you will see that the spot is moving. You can make a circle on the paper, same height circle, so that it occupies the sun's disk completely. And if you do that certain number of times, anyone can get the rotation of the sun, not only at the equator but also at some different latitudes. So that is, this method is called tracing. The other method is spectroscopic method. That there are line emission from the sun, and like when we say that there is a Doppler effect, anything which comes close to us, the frequency of that radiation increases, and anything which moves away from us, the frequency will, the wavelength will become larger, the frequency will get reduced, right? So that is called Doppler effect. So sun, because sun is rotating like this, so this part of the sun is coming towards us and this part of the sun going away from us. So if you take a line emission, measure the frequency of any line emission here and the same line emission on the other side, there will be a slight frequency difference. So that difference will tell you how much is the rotation of the sun. So that is called, it's a bit more complicated way to do it, but it is possible and it is being done. So any spectral line you measure, and because of the definition you can measure the rotation. This method in fact was developed by us largely, and this is we call flux modulation method. And this method is basically a very simple one, and can be applied to any rotating object. Like suppose I have this mark on my chest because of this jacket that I have, there is a line. And if I suppose go like this, and I come back here. So anybody can take, say, picture of me and compare the picture with the time, and from a distance, from any distance, when from he or she can see me, and when this mark reappear at the same position. So, or you can also do it the other way, that you don't record the mark, but you measure my radiation, the optical signal that comes from me. You put a photometer there, right? So, like suppose I open it, so there will be less light from this part, more light from this part, and this color will not give so much light. So if I rotate, that photometer will record the variation of light as a function of time. So because of the rotation, any radiation that come from a rotating body will have that rotation imprinted on this. So this method we call the flux modulation method. Any emission which is coming from the sun gets modulated because of the rotation. So there are large number of measurements that have been being done world over at various wavelengths from the ground as well as from space. And first we use the radio measurements of the sun, 2.8 gigahertz. Sun is measured every day at several observatories around the world. And when you simply plot that, take today, say 12 o'clock, the reading of sun at that wavelength, and whatever that number is, you put on a graph. Tomorrow again you do, day after again you keep on plotting. So you will see that the intensity will go up, will go down, will go up, down. So there will be, because of the local noise, radio noise, there will be some variation, but there will be, if the noise is less on the station that you are making the measurement, you will very clearly see that there is a 27 or 26 or 27 or 30-day variation. The radio intensity of the radio wave keep on increasing. So that is precisely the modulation. But this will be, if you measure the rotation from that, it will be slightly crude. So we developed the algorithm which we call autocorrelation. And that I'm trying to say. And this we use with radio frequency, with extreme ultraviolet, with X-rays. Any emission which is coming from the sun, and if you have regular observation of that, only thing that you require in this is daily observation. So at least, because sun rotates in about 25, 26 days. So if you take observation today and take observation after 30 days, then that rotation modulation will not be seen. It has to be, you have to frequently measure it. So if you do it daily, from that you can very reasonably, accurately calculate how the sun is rotating. So this part I think we have discussed. Okay, let me talk. That why we did the study of only coronal emissions. Because traditionally the sun was studied by optical signal. Because optical signal is very easily coming to us, and we can see that and make images. Initially people made images in fact by pinhole cameras. Like you make a pinhole and on the wall project when the telescopes were not there. And even in the pinhole also, some of the bright, bigger spots, you can see one there. And the first inference that the sun is rotating came out of such observation. And when Galileo made the first telescope, and by which they studied the sun, in fact he lost his eyes because of that eventually, because he worked very intensively on that. And he was the first person to scientifically prove that the sun's rotation at the equator is faster than so only the photosphere part was studied mostly. And the coronal rotation was low, because corona at that time was possible to be seen only during eclipses. and eclipse happen only once in a while, and that too total solar eclipse, which is even more rare and is seen for a very limited period at a very limited locations. So corona was not so well studied. So that was the reason. And the other reason is that from the ground, if you want to make the coronal measurement, it's very difficult. But now, with the advent of satellite, when the satellites are sent up in the sky, there are satellites which continuously monitor the sun 24 hours. They put at a point which is between Earth and the sun, that called Lagrangian point. A point which moves with the Earth and looking at the sun continuously, looking at the Earth also continuously. So such satellites have done very continuous measurements of the sun. And that's what we have used for this. And the analysis that we do is, like I gave an example, that if you take a photometer and make my video measurement and measure only the intensity from my body, and that intensity will have modulation, and from that you can determine my rotation, right? But that will be a bit crude because there is also reflected, scattered light from here and there. The photometer also will get noise. So to avoid that, we developed the method called photocorrelation. And this is basically an algorithm which is done by this method of computation. That you take the average of the intensity, you take individual intensities, take the difference, and take the next one, next intensity and their difference, make the product of these two and divide by it. So with this simple technology, what happens is that the noise part, whether it is because of the telescope, the observer, or because of the rotator or its surrounding, this noise gets sort of removed. And the autocorrelation coefficient will have such variations that it starts with 1, because when we say, and this that variable k is 0, at that time both these will be same and will get divided by the same square of the same number. This will give one number. So that will be 1 always. And then it decreases, becomes somewhat negative, and then again increases, becomes positive. Like that, this is the modulation of the solar rotation on the radio wave that you have measured. And then from here, because this axis has this lag, which is this k here variable, so sorry L here. So this L is this in days, so you can measure how much is the rotation of the sun. So lot of work on this was done by several of my colleagues, and you can do it at several different frequencies that get emitted from the sun. Thereby you can get the rotation different frequencies, and these different frequencies, radio frequencies, get emitted from different height in the solar corona. So thereby you can determine this is the height above the photosphere. This 5 into 10 to the power 4 kilometer, 10 into 10 to the power 4 kilometer, 15 into 10 power. And by different frequencies you find that the rotation decreases as you go higher. So the outer corona rotates faster than the inner corona. So this is the kind of research that you can do. Then this was done by radio measurement. There is no difference between the rotation to the latitude, the total emission from the sun. So that we call it the integrated emission. But if you take the image like this is a radio image, which is at 17 gigahertz radio image of the sun, and this is X-ray image of the sun. And on this you put line. These lines are the equator, 10 degree, 20, 30, 40, 50, 60 degree, different latitude. And what you do, measure the intensity at the near the equator every day and do the same analysis. So you will get the modulation, rotational modulation for equator, 10 degree, 20 degree, 30 degree. So at different latitude you can get the rotation and thereby the differential rotation. So this was done, and this is how it's done. That this is the actual measurement, actual intensity at say 20 degrees south in year 2009. The intensity, here also you see that there is a modulation. But on this, these are the noise. Some noise could be because of the sun, some could be because of our local animal, or some could be because of the instrument itself. So these noise will get more also there, but you can see that at some places where the noise is there, you almost get the rotation measurement there. But if you do pass the data to the algorithm, the formula that I showed you, then it will give you very clean modulational curve. And here you can very precisely calculate how much it will be. This is for 20 degrees south, and this is same thing for 20 degrees north. And you see that the modulation is of different kind. There is also a difference in time. So on different years also will be different. So like that you can do a lot of work. And this here as the example shown for the measurements by LOCO X-ray satellite during 1992 to 1995, which is one part of the solar cycle 22. The cycles also are numbered nowadays. We started with 0 in the beginning, and then every 11 years the cycle changes. Presently cycle 25 is going on between then 26 will be. So so here is the year. On this axis you have latitude, the 0 degree latitude of the sun, and this was the north pole, this was the south pole, and these color poles that you see here, the different color, are there representing the sidereal rotation period. 24, 25, 24 becomes by this color, 25 by this color, 26 by this color, then is 27, and red is 28. So you see, this becomes this way the time axis, this is the latitude axis, and there is a large variation. So if you take the average along the time, the rotation period at the southern pole is about 26, it decreases to about 25 at the equator, and then increases to 25.6. So this kind of variation. But interestingly, which was not known earlier, is that there is not only that there is a differential rotation, there is also an asymmetry. Like here, the rotation is large, here rotation is less on the two poles. So that tells you about the asymmetry of the sun. And this is for up to 92 to 96. Now if you change the year 96 to 2000 and plot the same way, here this is the time 96 to 2001, this is the latitude, 0 is the equator of the sun, north pole, south pole, and the color code is more or less the same. And you see now the average has become almost symmetric. So it was asymmetric. After 5 months, 5 years, it has become symmetric. And if you look at the next picture, which is next 5 years, 1990 to 2005, this is the year, this is the latitude. And in this, of course, since it is at 17 gigahertz radio measurement, we could not get the observations beyond 6 degrees. So the scale is slightly different. So, but in this, you find that the average rotation at the near pole region is about 26.5. It decreases to 24.5. The decrease is more here. And then on the northern side, it becomes 27 and a half. It becomes very large. So now there is again a asymmetry, but this asymmetry, the sign of the asymmetry has changed. In the 11 years before, this was more here and less there. Now it has. So that is also a temporal variability in the asymmetry of the solar. So many of these new things were discovered by these simple observations, simple analysis that many of my colleagues have done. This is in fact summary of what we have seen in that graph. That this is for this is the first part, first image. This that in which the southern part is higher, period is more, less in the northern is the middle part where it's more or less the same, and in the next 5 years or later it has somebody else. This is Jayadev's work, which he recently did, where he calculated this hemispheric asymmetry of rotation, and that is the time from 2008 to 2018 as this the temperature, because he used the images at different wavelengths. Madam, how much time it is now? Well, I think we should sort of find out, because then the students should get time to ask questions. So, very good. So, a lot of work in this that is being done. It's just very recent work where that with the temperature there is a variation of sidereal rotation period. Rotation, because depending on the temperature of the corona, the rotation period decreases. And this is the relationship between hemispheric asymmetry and the rotation rate. So let me summarize what we have seen here. That this, the coronal rotation has a temporal variability. It varies with time, and it has a 22-year sort of variation. Not only 11 years, after certain cycle there is a bigger change. And the corona does not rotate as a rigid body. There is a latitudinal variation of the rotation. Though the variation from equator to pole is lower than what has been seen in the photos. In the photosphere, you see the equator rotates about 25 days and the polar region takes about 35, 36 days. So there is a variation of about 10 days. Whereas in these measurements that I showed, there is a difference of about 2, 3 or 4 days. So there is a lesser differentiality, but at the equator, it rotates even faster than the photosphere. So, and then there is a what is called north-south asymmetry, and this asymmetry means that the northern and the southern have a different type of radiation. And that also, so a lot of work in fact is further needed on this kind of studies. I think this one will help. Thank you very much. What is this one? Maybe some. You will take. I also will take. So you can ask question on what I showed and discussed. You can also ask question on things that I did not talk about. Preferably space science. Right? Yes.
So like sun, do every other star emit heat? And if they, then how much amount of heat is emitted?
Say it again.
So like sun, it is a star. मतलब like
Sun is a star.
Yeah, like sun, do every other star emit?
Like all the stars you see in the sky, you see because they are emitting, and they not only emit optical signal that you can see with the eyes. If you put a radio telescope, there will be radio signal. If you put an X-ray telescope, there will be X-ray signal. Of course, there will be a lot of noise because of the local environment. They are emitting the entire electromagnetic radio to X-rays and all these stars that you see. The planets do. The planets do not have the source of energy inside them. Like all the planets like Mercury, Venus, Earth, Mars, Jupiter, Saturn, none of them, they all, we see them sort of reflecting sunlight. But because their own temperature is different, so we see them as a different.
Sir,
Yes. Yes.
Sir, how we come to know that what is inside the sun? Because we can see the surface of the sun and we can study that, but how can we know about it, what is inside it, and how we predicted that it's happening inside the sun? And how we come to know about the life of sun or the planets?
Very good question. See, like there is a seismology, a field by which we determine the structure of the earth. We also determine what sort of mineral, like the ONGC, which flows and gives us oil and gases. They use these helioseismic studies. The earthquake studies also are basically helioseismic studies. So they find the structure of the earth using that method. So on the sun also similarly, there is a helioseismology of the sun by which the interior of the sun is studied and you come to know. There is also a theoretical sort of studies, models that the astronomers or astrophysicists have made in the past, and from there they determine the age of the sun and the process that I described very briefly, which takes place in the interior, fusion reaction. Of course, fusion is a reaction which is also experimented on the earth. There are fusion laboratories in India. Also, there is one at Ahmedabad called Indian Plasma Research Institute of Plasma Research, where there is a tokamak and there is a fusion reactor. Though we have not yet succeeded, but trying to do that. Right? So with that, we estimate all these and also the engineering. Though it's a very complicated, complex process, which I also do not know very completely, but that is the essential.
And sir, when the sun's life will end, will it become a black hole?
No. Basically, to become a black hole, see, anything you can theoretically make black holes. Like suppose our Earth, there is a formula of escape velocity. You know that?
Yes, sir.
Which depends on the mass or the density of the object and also the radius. Suppose you increase the mass of the object without increasing the radius. Don't increase the radius but put more mass in the same radius. Then what will happen? The escape velocity from the Earth, which is now 11.6, right? It will become large and large. Or you make it compact, reduce the radius, keep on reducing. Reduce the radius so much that the escape velocity becomes equal to or more than the velocity of light. To make this, our Earth, so compact, keep the mass constant and reduce the radius continuously, and the escape velocity will keep on increasing. And once it increases to such a large number that the escape velocity is equal to or more than the velocity of light, then if you shine a torch upward, because light also has particles, so these photons will fall down because they are traveling with the velocity of light, and the escape velocity is more than that. So like we throw a stone here, it goes up and then falls down. So similarly, even the light photons will fall down. Then our Earth will become a black hole. So black hole is an object which is so massive that the escape velocity is equal to or more than the velocity of light. So any light that is emitted from there will not go out but will fall back. So that will come.
So may I Sir, first of all, thank you so much. You are saying
Isha.
Sir, I have so many questions. My first question is that
Maybe can you come here near? There is a way to, so that I hear properly and answer. That should be enough. That should be enough.
Sir, actually, lunar and solar eclipses happen. So, does it has any relevance to those mythological myths that we are supposed to follow certain restrictions, or like we are not able to eat?
Scientifically speaking, it's not relevant. Though, like